So just tell me to pass to the next slide.
Yeah, you can start over.
Okay, so I will go through the upcoming events of this meetup, and here you can see this is for the 2nd of April. This event is for the 7th of April. This all looks very interesting. This is the 16th of April, especially interesting event on quantum art and quantum metaverse. On 1st of May, Charlotte is here. Oh. And this is on 21st of May with Pawel, who is also from QWorld. And there are some follow-up events as well. You can check the group website and you can find the events there. And you can see the sponsors here. So QPoland, QMexico, these are the partners. And is there anything you would like to add, Hel?
Oh, no, thank you. Let's start it.
Okay, thank you. And let me just pass to the full screen mode. Are the slides changing?
Yes.
Okay, perfect. So I will start. Initially, thank you for the invitation. This is really nice to be here with you, with all of these participants. And I am Zeki. I am currently a doctoral researcher at Karlsruhe Institute of Technology, Institute for Technology Assessment and Systems Analysis, shortly ITAS. I am working on technology assessment for quantum technologies, mainly on different potential futures of these technologies and the conditions of these futures. But previously, in my previous life, I was a physicist. I had a BS and MS degrees in physics in Middle East Technical University in Ankara, Turkey. And also I was a PhD student there for quite some time, but then I switched sides and now I'm in a more social science background. And the reason I actually switched sides is I had a second master's degree in science and technology policy studies, where I studied mainly the policy aspects of evolving quantum technologies. Also, I am a board member of QWorld and a co-founder of QTurkey. And today I will mainly talk about our paper that was not so recently, but it is recently published, but it has been around for more than 1 year, titled A Computer Science-Oriented Approach to Introduce Quantum Computing to a New Audience, which is mainly a topic that we are interested under QWorld. It is an educational paper. It was published in IEEE Transactions on Education, and it is mainly an assessment of our introductory material bronze under QWorld, but also in a more general framework that we do not need to teach everyone physics for them to understand quantum computing. And this is not an original idea. It has been around for more than 20 years, but this is just a demonstration of that idea being applied to an educational material. If you have any questions at any moment, you can just ask. I'm okay with that. But also from time to time, I will ask whether you have any questions or not. And this is the outline of my talk today. I will start with an introduction. I will talk about what does quantum computers look like, which is really physics-oriented part, and I will talk about the background and goal of our study, and then I will talk about the bronze material and the approach that we are promoting, and I will talk about the methods and the results of the paper and a brief conclusion. You can reach out to me through these emails or through LinkedIn. I'm welcome to collaborate with or chat with you on any topics that are related to quantum. So I think this is known to almost everyone here. This is a figure or image from QEGYPT. This is the updated one. Just, it has been around for like a month. And here you can see national initiatives on quantum technologies, not just quantum computing, but quantum technologies in general around the world. And these initiatives usually cover like 5 to 10 years into the future. So most of these, or let's say some of these, will be until 2025, and some of these will be until 2030. So we can say that in the next decade, there's at least $30 billion of public funding allocated towards quantum technologies globally. And this number is expected to increase because, as here you can see, there are many countries that are just gray here, and they will soon develop their own policies or initiatives on quantum technologies, though maybe not in this scale.
Zeki, sorry, I have a question. So this
of course, Matt.
Does this include private industry or just
public?
No,
this is just public funding. I mean, for example, for EU quantum flagship, the assumption is that some of the money will come from private industry, but this is just projections, and it really doesn't cover any venture capital. It doesn't cover any private spending, in-house private spending like IBM's or Microsoft or Google or Thales or Atos. It doesn't cover those kind of funding sources. So this we can accept that this is mostly public spending in terms of promises, because yes, this is a promised amount, but unless this money is spent, we cannot assume that it is already spent. So this, as I said, this is a 5 to 10 year projection into the future. And here you can see some actual budgets. This is from the National Quantum Initiative in US. And here you can see basically a steady increase in the budget that is expected to increase until 2025, or let's say until 2023, and then it will be expanded for more than 2 or 5 years, and it will most probably be a 10-year program in the end. It was the original intention to make a 10-year program, but as far as I know, it was divided into 2 5-year programs. And it was signed into law in 2018. So the first iteration will end at next year. And one of the things that is also a topic here, and particularly interesting to us in QWorld, and I think to many of you here, especially who are interested in the education aspect, is the idea of a talent shortage, especially in quantum computing. So these numbers are again from QEGYPT. And again, this is not just in quantum computing, this is in the entire quantum industry. But here you can see that they are expecting, and this is the general expectation in the field, that the number of the actual workers in the quantum industry will increase rather rapidly in the following decades. And since most of these people need to have this very niche skills or talents in that sense, there will be some shortages. And here you can see these papers, or these news articles are from 2018, 2019. So this has been a topic that has been discussed for quite some time. And of course, this is really related to quantum computers in our case, because we are talking about introducing quantum computing to an audience outside of mainly physics, or any new audiences and diverse background. And here we have to consider, what does quantum computers look like, or do you really need to know enough physics to get into this field? So here you can see, these are very technical devices. These are very engineering-oriented devices, but these are not the computers. These are the cryogenic systems. The quantum processors are just the tiny bits in the end. These are for the superconducting devices. And here you can see some other types of quantum computational devices, like ion traps, neutral atoms, photonic devices. And here you can see these are actual physics experiments. These are very related to physics. If you, let's say in 5 years ago, you were talking about quantum computing without any physics, then it would be really, really interesting case, because most of the activities that has been going on in quantum computing for the last 5 years is very physics oriented. Just, you know, let's say mainly, because I will come to the point where we are getting outside of the field of physics and physicists. So here you can see, actually, this is from Google, and I think this is very explanatory in the sense that it is a very huge engineering challenge to make these devices work. So these are very high-tech devices. These are very engineering intensive devices. So these are not just, you know, plug and play, very easy, very miniaturized, or very ready to use devices in that sense. So when you can think that, you know, these are just computer chips, but to make them work, to make them into actual quantum computational devices, you need some very extreme physical conditions that are really hard to create under even under laboratory circumstances or laboratory conditions, and they are even harder to actually manufacture in a sense that are commercially viable. And here you can see this is one of the IBM chips, and here you can see the architecture, you can see the resonators, where the transparent qubits are. So these are, as I said, these are very engineering intensive devices. And this is from the experiment in China about the quantum computational advantage. Here again, you can see this is an actual physics experiment. This is not a computer. So they are planning to make this into a computer in 10 years, but nobody in their sane mind can argue that this is a computer. And here you can see the schematics of that device. So this is a physics experiment. This is not a computer. And there are actually very different ways to build a quantum computer or a quantum processor, let's say, or a quantum computational device. Superconducting qubits are the ones that are best known. They are used by IBM, Google, Rigetti, and many other firms. But they are not the only ones. There are ion traps, and for example, it's not included because this is an old slide from Riverlane, but Quantinuum is one of the big players here. IonQ is another one. So there are also big players in the ion trap game. But also there are silicon qubits, there are photonic systems, there are neutral atoms, maybe diamond vacancies. Nobody is sure, because, you know, diamond vacancies are really hard to make 2 qubits out of. You know, you can make really good 1 qubits, but it is hard to make 2 qubits out of them. And topological qubits, there's a real controversy here, so I won't be getting into this discussion. But there are very different ways to actually realize quantum computational systems, or qubits in that sense. And here you can see, this is from Dot Circuits. A couple of years ago, they did this wonderful work. They actually checked a lot of archive papers to see different types of hardware technologies that are being utilized. And I see somebody mentioning Bose-Einstein condensates. Sure, why not? I mean, I didn't actually see a company that is promising BEC qubits yet, but why not? We can also, I mean, you can realize a qubit out of any 2-level quantum system that is in accordance with the De Vincenzo criteria. So you can do that. So somebody is mentioning that they actually bought some INQ shares, so probably good for you. Let's hope that that it is a good investment for you. And so this is one of my things that I just checked from Web of Science. You know, what type of technologies that are being published on each year. And here again, you can see superconducting devices are, or the superconducting qubits in terms of publications are the ones that are being promoted the most. Also, there are photonic systems, ion traps, and topological qubits. And there are actually plans by companies to make these devices into, let's say, post-NISQ era. You know, make these into a post-NISQ devices, in the sense that they will have fault tolerance, they will have certain real advantages in terms of producing commercial value, solving some really useful problems, or at least they are promised to work in that manner. So that was the IBM's plan. This is Honeywell. As you know, they are now Continuum. They merged with Cambridge Quantum, but they are working on ion traps. Again, this is from IonQ. They are planning to increase their number of algorithmic qubits. And PsiQuantum is planning to come up with commercial quantum computers by 2025. And Google is also again planning to reach 1 million error-corrected, or let's say 1 million physical qubits with some error-corrected qubit capabilities by 2029. So that is not very far away. So there is a question, are these quantum computing companies solely focusing on hardware or software? No, there are quantum computing companies focusing on applications. Actually, we are just publishing, hopefully, I shouldn't say we are publishing, hopefully we will be publishing a paper on quantum startups, and there we actually checked the distribution between different subfields in the quantum startup ecosystem. How about Bose? Yeah, I think I answered that question, right? How about Bose-Einstein condensates? Yeah, so these companies that I mentioned, usually they are focused on hardware and software. But if you are doing hardware, you will probably be also be interested in developing some software. But there are certain companies that are only application oriented, and I think it is the important part in the ecosystem that will be requiring our kind of approach, in a sense that they will not be in a dire need to really understand the deep physics behind this, but they will need kind of a general understanding of the theoretical background of quantum computation. No, it's okay. By the way, I like answering questions. Do you think we'll? I have no idea. By the way, for blockchain or cryptocurrencies, I really have no idea. But I know there are a couple of people that are interested in this topic very deeply, and I see at least one of them in the upcoming events. So maybe you can ask Enrique. What error rate is related to which methods? There are very good papers on this, by the way. You can check some review papers on the error rates of different hardware structures. And also, if I'm not mistaken, Quantum Daily has this really cool table, but you can find it in different sources. And yeah, so background and the goal of the study. So the background is actually a story. In 2019 or in 2018, we had Abu Zarya Kalimas. So someone is trying to tell me something, right? Just playing with the screen. And so Abu Zarya is actually a researcher from University of Latvia, and they have this really cool team there under or in collaboration with Andris Ambianis, and they decided to develop this bronze material solely on the principles of using like Jupyter notebooks and using this approach that is not really diving deep into the physics, but it is looking from a more computer science, let's say, aspect or an approach. And one of the main reasons of this is that actually Abu Zar's background is in computer science education. So he actually thinks like in this manner, and I think it is very reflected in the materials that were developed out of this group. And they wanted to have this project called QDrive. They actually had this project called QDrive, where they drive around in different Eastern European countries, and they organize these free quantum programming workshops. And since we had previous connection, we invited them to Turkey. And they, of course, didn't drive to Turkey, they flew. But we organized one of the first ones of these in Turkey. And we actually, so here, after the first one, they tested in Latvia. And after that one, we invite them to Ankara, Turkey. And while there, we actually started this pre and post test analysis to actually assess the document. Because one of the discussions we had regarding this document is that, yeah, we will be organizing all these workshops, and now QWorld has been organized more than 70 times. But how do we know whether this is working or not? I mean, yeah, people seem happy about learning this stuff, but are they really learning something? So we wanted to actually keep track of whether this document or whether this education material is working or not. So that was the idea, and here is the first workshop that it was implemented. Here you can see it is 2019. Good times, like pre-pandemic. And later we translated this into an actual paper, and the goal of this paper, or the, let's say, goal of this study in this sense, was to inform academics and organizations interested in introducing quantum computing to a diverse group of participants on an educational approach, and it is intended that the proposed methodology would facilitate people from diverse backgrounds to enter the field. The reason we are stressing upon the diversity aspect here is that, as you can see, there are many countries that this material was presented in and the workshops were held. And later you will see that the background of the participants are also are not very monochromatic. They are not all physicists. They are not all computer science students. They are not all from the STEM fields in that sense. And what are your options? By petaflops, do you mean what do you mean by petaflops? I know the computational unit of flops, and petaflops is just, a lot of flops, but how does it relate to quantum computing? I don't know. By the way, I think this is a good question, by the way, regarding the comparison of high performance computing devices and quantum computational devices. And there is this really cool efforts that has been going in the Yuli supercomputing center, and they are working on this QTRL thing. So TRL is technology readiness level, and QTRL is quantum technology readiness level, and they are doing these benchmarking efforts for different quantum computers or different quantum computational devices, and they are trying to figure out certain numbers in terms of like this device is under for certain problems under certain conditions is as powerful as this classical corresponding device. So this is a benchmarking effort, and for the person who is asking about petaflops, I would really recommend for them to check these HPC benchmarking efforts. So there has been quite some events or activities in increasing quantum awareness because of the same reason that we were also involved in as QWorld, because there is this expectation of a talent shortage, and also a talent shortage means that there will be an opportunity for people from the developing world or from certain marginalized backgrounds to get into this field. So in that sense, we really want to increase access to these technologies, not in the sense that everyone has access to IBM devices. Just because you have access doesn't mean that you will be able to use them. You need certain, let's say, background information or some certain base level of skills that you require, and to obtain these skills you need educational efforts, and there are different educational efforts. Like KIT has a textbook that is really good, and also they are organizing global summer schools, and they are also producing these really cool tutorial videos and courses. And also there has been this great effort by Qubit. And also we were also involved with Microsoft in QTurkey, and this quantum KIT-ITAS approach is really cool. And there are other efforts like Quantum Quest. And here you can also, this is from a paper that was recently put on arXiv, and hopefully it will be published soon this is from, again, I think it was by a team in Kureka. And here you can see, by the way, let me check the chat as well. Qubit can be, okay. So people are also chatting in the chat, and it is really cool. People are answering each other's questions. And here you can see actually some different, not approaches, but different things, different elements of the ecosystem that are essential for increasing quantum awareness and also preparing people for the upcoming industry, let's say this developing field of quantum industry. Because in the industry, people will require, in a sense, that, let's say, a flow of new incoming potential people that they can either collaborate with or work with. So, sorry, I just muted someone. And here you can see there are certain workshops, events, online courses, games, community building efforts. There are many different players in this great ecosystem, and QWorld is just one of them. And there are really so what was the saying? It takes a village to raise a child. So it takes an entire ecosystem to raise the future of the workforce of quantum industry. And also it's not just, in a sense, workforce. We should enable and empower people in a sense that they should be able to use these devices or get into this field if they are really interested in it. So under QWorld, what we do, we work for popularizing quantum technologies and quantum software, and for involving more people to the field by working publicly and or academically and locally and or internationally. Who we are? We are a global network of individuals, groups, communities collaborating on education and implementation of quantum technologies and research activities. So you can check us out under QWorld.net. I believe that we are doing cool stuff, but you are of course free to make up your mind. And the bronze material is the first material that was produced under QWorld. It is a really introductory material for quantum computing. It contains some theoretical background. It consists of Jupyter notebooks, which was kind of a new thing like 4 years ago, but right now it is pretty much the standard of the any educational material. It is on Qiskit, so the practical programming tasks require you to work with Qiskit. That is the IBM's. I mean, everybody knows Qiskit right now, so it is the IBM's software language, and it is built upon Python. As a prerequisite, we only require you to know basic linear algebra and some Python, so that you can work in Qiskit. So until now, we can say that the Q bronze or the bronze material has been implemented in 73 workshops in 27 countries, and more than 3,000 people completed the workshops. And by completed the workshops, we mean they actually attended all the courses or most of the courses, let's say more than 70% of the courses, and they completed the homeworks that we assigned them. So we do not just hand out diplomas to everyone that are registered. So you can actually check the bronze material yourself. It is open to everyone. You can find it in our website or GitHub. And the main approach here is taking the bits, introducing probabilistic computing, and then just introducing quantum computing. And we are using an abstraction through linear algebra. It is now a very common thing in the field, and we do not use complex numbers within bronze because we don't actually need to. Just by using negative numbers, you can introduce the concept of phase. So as I said, this was not an original idea by us. Here you can find a really good quote by Scott Aronson. So quantum mechanics is what you would inevitably come with if you started from probability theory and then said, let's try to generalize it so that the numbers we use to call probabilities can be negative numbers. As such, the theory could have been invented by mathematicians in the 19th century without any input from experiment. It wasn't, but it could have been. So in that sense, if you are learning quantum mechanics, let's say during your undergraduate studies, I think you can safely understand that the math behind quantum mechanics doesn't require much physics. So the physics of quantum mechanics requires this really cool linear algebra oriented Hilbert space math, but the math behind it doesn't require physics in that sense. And when you are thinking about quantum computing and quantum computation in a theoretical sense, if you accept that certain quantum mechanical phenomena or properties are given, you do not need to know any physics to actually implement them in terms of an algorithmic thinking or on a software level. So the content of the material is very simple. We introduced basics of classical systems, basics of a quantum program, basics of quantum systems, quantum operators on a real-valued qubit, entanglement and certain protocols, and Grover's search algorithm. And again, as I mentioned, as a methodology, what we did was we used a single group pre-test, post-test design that was implemented in 22 workshops with 317 participants. So the participants fill a participation form and satisfaction form before and after completing the workshop. We identified ID numbers to the participants, so the outcomes are anonymized. So we do not say that, you know, oh, you learned or you somehow didn't learn. We didn't want to make anyone feel good or bad in that sense, because we were only interested in whether the education material is working or not. And the participation form includes demographic information such as age, department, gender, and education level. And the satisfaction form includes certain questions about satisfaction from the workshop. And a test about quantum computing is answered by the participants in both surveys to measure knowledge acquisition. So the pre-test and post-test, the name is very self-explanatory. You can use the same test before and after to see the difference. And here you can see some basic information regarding our workshops. And let me check the chat. Do you still use bracket notation for qubits? Actually, not necessarily. We are using the vector notation mainly. You can use the bracket notation, by the way, if you introduce it in a manner that is not confusing. Because it is a shorthand notation, it actually takes more time to write the vectors each time. But if you are using something like a Jupyter notebook, then you can just use the vector notation. Okay, I'm checking whether there are any other questions. Okay, there are no other questions towards me, I think. Hello, negative, how to students? I think this is a good question, by the way, allowing negative probabilities. Actually, you need to introduce the idea of probability amplitudes, and then you can show them so basically what you can do is you can show the concept of negative probability in a sense that does not violate their understanding of you know, how probability works. And you can do this by using the analogy of coin flips. And so one of the things that is important when you're introducing quantum computing or qubit as a concept is that people should be able to understand the difference between different qubit states in a 50-50 sense. Like you cannot just say that, oh, there's a qubit and it is 50%. It gives you 0 with 50% chance and 1 with 50% chance or probability. You cannot say this because it is not a really valid way to introduce a quantum state. In a quantum state, you have to be able to distinguish between, you know, 0 plus 1 divided by square root of 2 and 0 minus 1 divided by square root of 2. And you should be able to convey this message to them. And in that sense, they need to understand the concept of probability amplitude and, you know, in a sense, negative probabilities. Because otherwise, if you do not stress upon this topic, they will just be thinking in terms of probabilistic bits, and you cannot do destructive interference with probabilistic bits. You can only do constructive interference. And although it might be beneficial for certain things, it is not quantum computation. Then you do need complex number notation. No, you don't need to. You can mention the complex numbers, but you don't actually need to introduce complex numbers. I think there was a really cool theorem on this. You can just use negative numbers and you don't need any complex numbers by just increasing the Hilbert-Space dimension. Can you name any real QC practical application existing? I will leave this question to someone else because I'm sure there are more qualified people here to name real practical applications. And let me check the questions. I have a quick question. After learning some basic stuff and quantum computing, and then how to use it on a specific application, because each person comes from a different domain, how we can utilize QC in application oriented. For example, I am from mechanical engineering. I am doing masters in computational engineering. TU Dresden. Good. So, I think this is a good question, by the way, how to learn to apply what you learned in quantum computing to specific questions. And I'm sure there are other talks that can help you. As far as I can say, what you need to do is to actually not start from the quantum part, but check the questions, dissect them into certain mathematical processes, and then check whether any of those processes would or can be transformed into a quantum computational process, and if it can be, whether that process can be transformed into a circuit design, and if that can happen, then check whether that circuit design can actually be implemented, and if it can be implemented, whether it provides any advantage or not. So it is a long process. It is not a very straightforward thing, and I don't know any methods that will show you whether any problem automatically gives advantage or not, because I don't think such a method exists. It is very dependent on the type of your problems. Somebody gave an example, like practical applications are in logistics. Sure, why not? Yeah, so I think it is a good discussion there, like quantum machine learning, classical machine learning, like VQE, QAA. These are real research topics. It is not like there are people that know whether they will work or not, and then people are doing stuff on it. People are actually really researching and trying to answer the questions whether it will work or not, or if it is going to work, what will be the actual advantage, how can they work in certain conditions, and how can they be developed under other. How do you introduce negative amplitude? You just expect them to accept that there is something called a negative amplitude, and if they do not accept it, then you show the exercises, and I think they need to be able to see that in terms of, let's say, block sphere exercises, because just mentioning it in an abstract sense, I mean, people can accept it, they can just say that, oh, this is the math and I will live with it. But if they are using certain block sphere oriented exercises, then it becomes more understandable. But to be honest, in the end, you just expect them to accept that things such as negative amplitudes exist in a quantum computational system. You can create these, and as you create these, you can work with them, and as you work with them, they can actually allow you to create certain scenarios that were classically not possible. When a measurement is taken, you square. Yeah, of course you say that, but to be able to say this, you need to again introduce complex numbers, and you don't need to. Yeah. Okay, so I will continue. And here you can see the most of the workshops, or all of the workshops, were pre-pandemic times, and actually we stopped as the COVID-19 situation started to take over. And here in the right you can see the distribution of ages, gender, and educational background. So the tests were just some Google forms, and the knowledge test was actually not that complicated. Like, what are the two fundamental quantum phenomena that differentiates quantum computing from classical computing? This is a checklist question, like very simple questions, some not so simple questions, like the matching the quantum gates with their matrix representations. But they were, in a sense, testing very simple or low levels of knowledge retention. And for methods, we used some statistical methods. I wasn't very involved in this part. And here you can actually see the test scores of all participants before and after the workshops. For some weird reasons, some of the participants forgot what they previously knew. It was an interesting thing to see. So here you can see definitely there are some outliers. But in general, again, you can see that between the pre-test scores and the post-test scores, there was this considerable gain. And one of the things that we were able to show is that there was no considerable difference between the gains of different groups. So here you can see computer science students, physics students, I shouldn't say students, people with computer science background, physics background, engineering background, science background, and humanities and social science background. And here you can see the pre-test and post-test results, and you can actually compare the gains. And here you can see that, yeah, of course, the gain was the lowest for humanities, but again, you can see they came with the least amount of knowledge, and they also learned, in a comparative sense, almost the same with computer science students, computer science participants, physics participants, engineering participants. And this is the satisfaction test that we later ran. So the question numbers here are in reverse. So the question 9 represents to this one here. And again, this was important for internal sense, because we were able to identify which part of the workshop works and which part of the workshops didn't work. And for example, one of the things that we find out was that the time to think through the tasks and problems by participants has a really wide variance. So here you can see the mean is over 4, but for some of the participants, the time was not enough. And one of the things you should be careful about when you are developing these educational materials is to consider that, you know, there will always be, or probably there will always be, some participants that the time is never enough, and you should actually look at the mean and see whether it is working for most of your participants. So this was one of the things that we really had to work on, because, you know, when you encounter certain feedback, your initial instinct is to just to give people more time. But if you check this, you can see that for most of the participants, the time is more than enough. The other parts were just mainly very stellar. So the conclusion, the proposed approach is appealing for an audience who does not want to learn quantum physics or will not need such understanding and facilitate increasing quantum awareness among the diverse group. So this part is actually rather important in my opinion, because we also had this open-ended questions in the end, and we gathered those questions. And one of the most common feedback from physics let's say participants with physics background and electronics engineering background was that we want to see more physics parts implemented in this educational material. But none of the other participants asked for this. So when you are developing an educational material and you constantly get feedback on you should introduce this, you should introduce that, you should be careful to actually identify what type of suggestions are coming from which background, or who wants what is a really valid point when you are trying to develop these educational materials. Being introduced to quantum programming is another educational attainment of the approach, contributing towards the endeavor to prepare for the future work quantum purpose. So this is again kind of important, because usually the idea is this: you first introduce quantum physics or quantum mechanics, and then you introduce quantum computing, and then you introduce quantum programming. But in this sense, or in this approach, you actually mainly introduce everything through quantum programming. You expect your participants, your students, to not to learn everything and then start programming, but start programming and learn through that programming. And outcomes revealed a significant increase in knowledge retention for participants from diverse. So I just covered this earlier as well. Here you can see we have some additional educational materials, Q nickel and Q silver, that are on the follow-up levels in a sense. So it was the Q bronze was the introductory level workshop, so Q nickel is the elementary level workshop, Q silver is the intermediate level workshop, and hopefully there will be like Q gold, Q platinum, etc. And this paper came out of our project. So there is this Q intern project that we are running hopefully every summer, and each summer mentors can come up with certain projects that they want to run, and we match them with students that are willing to participate in their projects. And for this project, so we had the data, but we needed to analyze it, and one student actually helped us to analyze the data, and she's also introduced. She's also a co-author of this paper, and Özlem is actually she is the first author, and she is the main instructor that gave a considerable amount of these workshops. So she had that experience as well. Okay, so here, so Ilknur was the student or the Q intern that helped us analyze the data, and Özlem was the main instructor for a lot of these Q bronze workshops. And here you can actually reach out, you can check the paper. And here are some funny things related to quantum, so please don't misuse the word, and I will be answering your questions now, so thank you. Let me check the chat, because apparently there are 12 chat messages. Okay, I will start. Have you compared your approach with other approaches? This is a very good question, by the way. No, we haven't, and we would really like to do that. but for that we need common assessment tests. So one of the problems here, and not just with us, with other educational efforts as well, there is not a test that is applicable to all materials. So for example, for our test, of course we tested regarding to the things that were aimed by the material to teach to the people that are participating in the workshops. When will we have Q Platinum or Q Gold? Hopefully soon. And by soon, I mean end of this year or next year. You should definitely ask the Q education department. How do you measure knowledge retention rate? So again, it's a good question. So by this pre and post tests, we have we actually have the data of the individuals, and then you run the analysis that I showed regarding this. So there are these different statistical tests that you can run on this data to show whether any significant gain is obtained or not. How much the workshop cost? Again, this is a very good question. One of the things under QWorld is that we do not charge any of the participants, and everything is voluntary. So it actually didn't cost anything for the participants, but of course we need a place to hold these workshops. We need to be able to give people certain beverages for this, and people are we need to print some stuff, so there are some costs attached to this, and for that we actually got some individual sponsorships from certain places, like certain technoparks and universities, and sometimes some companies helped us, but mainly it was a cost-free and voluntary effort and almost all of the 70 workshops were organized in this manner. Yeah, definitely. So as I mentioned, so David is pointing out to a very good thing. In IBM Qiskit Summer School 2021-2022, we never introduced quantum mechanics either. Yes, so now this approach is actually a very common approach, but not that this material was produced into 2018. So that was the thing. Back then, the main argument was, or not say main argument, but the main approach of the books or courses on quantum computation was to introduce the physics first and then pass to the computation. But as you mentioned, the Qiskit textbook as well is not very physics oriented in that sense. So this is a very common approach right now in the field. And I think this is why we need some common assessment criteria to compare between different workshops, different educational efforts, and to actually improve what we have. I know Qubit by Qubit is doing a wonderful testing and data gathering in their programs, but we should see what they come up with. I'm teaching a college course with the same goals as your materials. I have two questions. For an algorithm like Doge or Grover, the math proves that they work, but how can you teach intuitive ideas about why they work? This is a very good question. How do you create programming exercises that are more than just copying the known algorithms? Again, this is a good question. So for the first part, I think one of the things that we should mainly aim at is these workshops are just introductions. So nobody can learn quantum computation in 3 days. So in that sense, what we need to do is to give people the capability to be able to explore further by themselves. So we should not be aiming to teach people, even in just a semester to understand the intuitive ideas behind these, especially if they are in undergrad, very quickly. But we should empower them, and they should be able to explore further with the with what they got from us. So that's the point. And the second is, how do you create programming exercises that are more than just copying known algorithms? It is a good question. One thing is that you can actually take known algorithms and just remove certain parts and expect participants to fill those parts by themselves. And in this sense, the exercises are not that long, but people can kind of show some creativity there if they do not know the algorithm, and mostly they do not know the algorithm because this is an introductory level workshop, and people coming to this workshop are not very familiar with the known algorithms in that sense. But to create truly novel exercises, then yeah, you need some experts in that. And hopefully some of the people in the Q education team are experts, and they are working on developing certain new and novel things. But I think for introductory level exercises, you can just copy the known algorithms. Let me see other questions. Are Q intern? Yes, it is remote, so it is not funded. As I said, most of the things we are doing are, almost all of the things we are doing are voluntary. Even now, most of QC people are from physics background. We need more. I definitely agree. So that was one of the points that we are trying to push. We need more people from not just computer science. We need people from a diverse background. And I'm not saying this just in a sense that, all diversity is good. We need people from diverse background kind of sense. We really need people from fields like chemistry. We need people from different fields of engineering. We need people from finance. We need people from statistics. We need people from many different fields, because as it is hard to accept by some physicists, and as I was mentioning, I also feel like a physicist in most of the time, we do not know everything, and it is really hard to actually see or to learn what is important for other fields. So what is important for us may not be important for chemistry. And I think this is very evident in the field of quantum chemistry. They are still working with DFT, and they are very happy with working with DFT. So we should actually lure more chemists into the field so that they can develop certain algorithms and certain easier tools for other chemists to use. And that way, quantum computing can become something that is not just reserved for physicists or computer scientists or quantum information scientists. I don't think we need Elon Musk for everything, by the way.
One more question from YouTube. Somebody asked from YouTube, has there been any interest in starting a Q America cousin?
If people are interested, why not? So mainly we are targeting, actually we are not mainly targeting anything. We are going as we encounter interested people that we can actually trust in, because these communities are local communities. QTurkey is run by people in Turkey, and QPoland is run by people in Poland, and QZimbabwe is run by people in Zimbabwe. So, or people that are associated with those countries. So in that sense, if there is a Q America, we would really love there to be, but Yeah, why not? And one of the reasons that we mainly expanded into certain countries is that, you know, like in Germany, there are many efforts to introduce quantum computing or quantum technologies to the public that are already supported. But in most of the countries that we are active in, there are no such coordinated efforts. And in that sense, I think community building is more valuable and produces more empowering outcomes, let's say. But for US, I'm sure there are really cool efforts in that as well. Yeah, David Lewis, I think definitely right. In US, there are many efforts, like qubit by qubit is an exit. You know, they are doing an exemplary job. How we can observe entanglement? Is it proved and working in our? Yes, it is. It is definitely a physical phenomena, and it can be created in quantum computational devices, both in superconducting devices, and so any device that you can perform 2-qubit gates, hopefully you will be able to get entanglement. Oh, this is a good question. Any plans on consolidating the material of the Q-bronze, Q-nickel, and Q-silver with more visualizations and more explanations into a book? I honestly don't know. And I honestly don't know whether we need to or not, because there are some really good books out there. And yeah, if someone is interested in doing this, again, I'm not in the Q education department, and so under QWorld we have some certain departments that are dealing with different activities. So I'm under Q Cousins department, and yeah, so there's another question. Yeah, for a book proposal, I think Q education department is the people, or is the place where the people that are interested in or in charge of this thing are. Sorry, I need to drink some water. Yeah, entanglement has been applied in secure communication in real life. It is applied in many things. So entanglement is real. If someone is telling you to, you know, be skeptical about entanglement, you should probably not trust them that much.
No, I'm preparing master degree, but I'm struggling while explaining.
Explaining?
Yeah, like in chatting, not in serious class. They just can't absorb the idea because they studied classical computers and computers.
Yeah. I think you're definitely right. So in that sense, again, this comes to the question related to negative probabilities as well. For some of the things, while you are introducing them, you should, so one of the terms that our professors used to use was, you should just convince yourself. So just convince yourself that entanglement exists, or just assume that entanglement exists, you know, test it, and if your tests or outcomes are not in accordance with your assumptions, then you can basically argue that entanglement doesn't exist. But if you have access to certain experimental devices, especially some photonic devices that can generate entanglement, then it would be really easy for people to believe that there is a thing called entanglement. But one of the things that mainly both participants of workshops and students need to understand is that entanglement and some other quantum phenomena, they don't have any example, they don't have any counterparts in classical physics. So even by analogy, they are not really going to be able to explain this. So they need to understand the phenomena itself, and they do not need a classical correspondence in mind to be able to understand entanglement. And again, yeah, you should definitely check Qiskit, or you should definitely check. There are many wonderful visualization efforts that are aimed at introducing these quantum phenomena in a sense that is understandable by most people. And also maybe they can just check certain quantum games and interactive tools, because I think those will also be able to help a lot. Actually, let me just share a list, because we had a we had this paper recently, and you can actually check the paper. There are many tools that are being used now to introduce such concepts to general public and to newcomers into the field. So this is another approach, using such visualization, gamification, and other more, let's say, variable tools or interactive tools or online tools to introduce these concepts. So there's this entanglement will be the reason because there will be no quantum internet, no quantum Google, there will be no advertisement. I don't know. Yeah, by the way, watching Qiskit's YouTube videos, they're pretty solid way to start. They are really good. Any other questions? By the way, I can share the website. So that people can easily find out. So here you can actually just check different projects that we have, like QDrive, QPool, QIntern, and there are different QTraining events as well. And under research, you can find different research projects and study groups. Under QEducation, you can find different courses that were started, some recently. And under QCousins, you can find different cousins. And under events, you can find these different events organized. So if you just go to QBronze here you can find, you can actually access different versions of the bronze material. So there is this one that was created in collaboration with IBM Quantum, and it is called Bronze Qiskit. And there's another one called Bronze Project Q that was created with the support of Pawel, and here you can find it. And you can see the organized events here. And you can actually check different activities as well. So if there are no other questions, maybe Helen, I can just go over the PDF that you sent. Why Q Germany is not there? Because no people from Germany wanted to form this. But by the way, I think it is really hard to organize such things in Germany because there are some obstacles here. But yeah, if people in Germany are interested in this, why not? What challenges are QWorld face? So what do we face? Okay, so maybe I can quickly go over the PDF to again introduce the upcoming events, and then I can answer the question by David, because I think it's a good question. So let me check whether, yeah, so you can see it, right? Can you see the screen?
Yes, I can see it.
Okay, perfect. So the next event is April 2nd. Here you can see, and the time is also here. Yeah, so the following event is on April 7th. It is on quantum teleportation, and it is by very cool people. And on April 16th, there was someone asking about the blockchain and cryptocurrencies. You should definitely ask Enrique. He's interested in that. And the following event is on May 1st. Shaddad is also a very cool guy. And here, this is on May 21st. Pawel is the founder of QPoland and also a board member of QWorld. And okay, I think this event is by Pawel. Yeah, so this is from Warsaw Quantum Computing Group. This is for the Quantum AI Foundation. And yeah, so these are some events that are associated with the group. Okay. So the question by David, I can answer it. What challenges do we face? I think one of the main challenge in the community building sense is the challenges that come from community building, because it is a mainly volunteering effort, and there is a huge, let's say, so there are people that are interested in it, but not that much. So they come in and come out, you know, they join the group and then they leave the group. So you need to be able to deal with that, you know, influx and outflux, you know, this flow of people. And also you need to be able to actually assess what you are doing, whether you are doing it correctly, whether it is actually helping the community, it is actually serving the purpose, serving your purposes. So one of the things that we are really interested in is to reach the people that were in otherwise had a low chance of encountering these materials. So this was one of the things that initially we got involved in. And remember that this was pre-pandemic and we were doing on-site events. So we were actually planning to go all these other countries. And we actually visited a lot of countries as well. So after this all online emergence of this online world, or the increasing of the number of these events, I think it actually kind of helped a lot in a sense, because it enabled emergence of global communities, but in a sense it also loosened the connection between people, because previously you were organizing, you know, on-site events, people were able to meet face to face, and it is always, I don't know whether it is true or not, but I think it is always better to meet with people face to face while organizing such events. But it is definitely a huge advantage in terms of a global setting to be able to organize online events. And I think one of the really good first examples of this was the KIT Global Summer School. I think it was in 2020. And I remember that, you know, because people were applying from our side as well, and then they, you know, transformed it into an online event, and it was really successful. And then people realized that, oh wait, we can now do these huge online events that are globally accessible, because the only limit is the time zones. And I think that's really helped. But one of the things is that just because people can use these devices, or just because people can access these educational materials, it doesn't automatically empower people, and it doesn't automatically make it a democratic process. So we need to be able to face these challenges as well. Just because people can use certain devices doesn't mean that they have access to these technologies. So we need to find, as a community, and not just QWorld, as this entire quantum computing community, we need to be able to find ways that truly empower a global community, in a sense. I think that is the main challenge that we all face, not just QWorld, but it is a global challenge in a sense, because, well, this is weird to say, but thanks to the pandemic, this entire thing became global. And yeah, that's a very good paper, by the way. And yes, we need local organizations. We need, so there's this term glocal, like it is global, but also local. So there needs to be these glocal organizations. Can you give examples of quantum computers already in use, and what new way humans implement it? I think we covered this, right? There are really good papers on this. Maybe I can share a special issue in this, because I really like what they are doing. So there are some papers in this special issue. You can check. There are some different quantum industry applications there. I hope it helps.
I have a question. Why don't you just consolidate all the Q cousins together into one group and host a single online class, and so that people can learn at their own pace?
We actually have certain, now we have, let me just mute there, sorry. We have Q course, and everybody is welcome to join everything that most of the groups are organizing. But for example, in QTurkey, we are organizing most of our efforts in Turkish. So, I mean, yeah, we can organize everything in English, but one of the things that we need localization for is that there is already enough materials in English, I think. So this is a little bit counterintuitive in a sense, but there is also enough material out there in English, and it is really good that they are out there. But just translating those into local languages, again, it doesn't help a lot. It helps considerably, but there needs to be people that have the capacity to actually convey those messages in a local language as well. So, and it is not only related to the language too, because each country or each cultural background has some certain slight differences in learning or what they're interested in, you know, and when you think of all of these things, and you cannot think of all of these things simultaneously as a, you know, just a community builder or just someone that is interested in quantum computing, then I think it really helps to have these local organizations, because then these local organizations can actually work on this, and if they're interested in doing anything global, then they can just use the other networks that there is all, you know, like QWorld, like your network, like Qubit by Qubit, you know, they can just get integrated into those networks, because as far as I can see, the quantum community in general is a very welcoming community still. So it is not like some other communities that certain fragmentations are happening and people are taking stances against each other. So as far as I can see in the community, there is this real feeling of solidarity, and people are trying to help each other, and people are trying to make this technology work and make this technology work for everyone. I hope that I'm right. Yeah, so there was this comment on hybrid conferences. I think organizing hybrid conferences is a really good way to make it to the end of this pandemic, but trying to keeping the online element of these events. But it also has its own entry barriers, let's say. So not everyone can organize hybrid events. It requires certain technical skills, and I think people should, especially in the field of community building or communities, people should be able to start building those capacities into their organizations. So if you have any other questions, please feel free to ask. Okay, I think we are done, right?
Yes. Thank you for coming.
Thank you for inviting me.
So if you still have any question, please feel free to unmute and ask. If not, we can end this meeting. Thank you.
Yeah, I have a question about the notebooks. Do you put them on GitHub?
Yes, yes, both versions are on GitHub.
So
Both the Qiskit version and Project Q version.
is there a link to that?
Yeah, of course, let me just share it. So this is for the Qiskit version, and this is for the Project Q version.
Thank you.
Thank you.
Do anyone still have any more questions? If not, thank you again for coming.
Thank you for the invitation, and thanks to everyone who joined and asked wonderful questions and became part of this.
One more question from YouTube. The materials of what was done or some activities are on the QWorld website yet?
Yeah. As I mentioned, as I shared the website and the links, and also maybe let me just share this in a general sense, and you can copy paste it to YouTube. I can share the Q-nickel and Q-silver as well, because they're also on GitLab.
Somebody give a nice comment. Thank you for the presentation and the section. That concludes our event for today, and I hope Zeki will come back and talk about something new. And one more question.
Yeah, sure.
Are there QTurkey quantum gate projects?
I have no idea. Do you mean QTurkey by not qubits, but using QTurkey? So for those who doesn't know, QTurkey are 3-level quantum systems. The math is there. If anyone is interested in developing a material using QTurkey, I think they are free to do so. But one of the problem is you would not be able to actually implement those, because QTurkey are by definition different than qubits, and you cannot implement QTurkey based computational circuits to qubit based circuits. But the math is there. You can actually do it.
Yeah. Hello.
Hello.
Yeah. Could you explain how the two technologies, quantum and artificial intelligence, will work in industrial practical oriented? How these two technologies will work?
There is this field of quantum machine learning, and yes, so Matt shared a paper on qubits, so any D-level qubits, or not qubits, but any D-level systems. So there is this field of quantum machine learning, and of course I'm not an expert on it, so I will only be able to speculate a little bit. As far as I know, there are these methods like variational quantum eigensolvers and quantum approximate optimization algorithms, and these are using certain hybrid models to train or to actually create quantum circuits using machine learning. They are having these different circuit types, and that there are certain parameters, and then you are feeding data into it, and then you are training your system to actually find an optimal quantum circuit, in a sense. There are, of course, many other applications. As I said, I am not an expert, so the only things that I can advise you to check are these two, variational quantum eigensolvers and quantum approximate optimization algorithms. But I'm sure there are many other applications, because especially ML and AI are really huge topics right now, and quantum computing is like a very small field and niche field compared to those two, because especially AI in general and ML in particular are, they are huge right now. And also, yeah, there are these things like, QNLP, so quantum natural language processing. Let me just share a paper on that as well, because I think it's a very cool emerging topic. And if you're interested in this, maybe you should also check Zacac's calculus papers, because I think they are really related in reducing the complexity of certain algorithms. I really don't know, and by don't know I mean this is a very so for those on YouTube that don't see the Zoom comments, any discussions about future bio-quantum computers, whatever there may be. I know there are discussions on biocomputers like DNA computing or certain protein imprinting. But for bio-quantum computers, I don't think so. Maybe in sci-fi work, because it is still a very widely debated topic that whether any biological system has any discernible quantum properties other than very simple things like birds' eyes using certain entanglement distributions, like to align themselves with respect to the magnetic field, stuff like that. For biological entanglement, the only thing I know is the recent tardigrade paper, which was, really debated in a sense. When is the next QBronze Q-Silver? Okay, this is a question that I can answer. For the QBronze, we have let me check whether this is still open or not. Okay, so the applications are still open for this one. Let me even check the Poland one. No, some of the applications are closed for this one. So in this spring, so in the next couple of months, we will have this period called Q Spring, and there will be many events organized by different Q cousins during this period. So I just shared one of them, but this is not within the context of Q Spring, but there will be several Q Bronze, maybe some Q Nickels, but certainly Q Silver workshops that will be organized in the coming months. So if you're interested, you should definitely follow some of our social media accounts, because we are announcing them. And by with diploma, you mean, yeah, we give out certificates at the end of these events to the participants that actually both participated and completed the assignments. So at the end of each session, let's say, we assign these homeworks, and these homeworks are usually we are using a system called Canvas, and you need to complete these assignments with a certain degree, like you need to complete at least 70% of them. and you need to complete them in time to be eligible for getting this certificate. But if you just complete the workshop and do the assignments, then of course you will get the thing called diploma. Thank you. We are also looking forward to you.
Yeah. Sorry. Could you please again explain what is the difference between the Q nickel, Q bronze, Q intern, Q spring?
Yeah, of course. So lots of things with Q. So Q bronze is the introductory material. It starts with very simple things and it ends in Grover search algorithm. And then there's Q nickel. It is a very intermediate material. You can actually, let me again share it. You can check the content here. Here. It actually covers some conventional algorithms and like max cut problem, again with Grover. It is a very intermediate thing. And there's Q silver. Again, let me share it here. No, this is again nickel. Sorry. And here we actually introduce complex numbers, block sphere, operations with complex numbers, and quantum Fourier transform and Shor's algorithm. So by the end of Q silver, you reach to a point where it is kind of similar to a one semester quantum computing course, because usually at the end of these courses people reach their point where they covered Grover's algorithm, Shor's algorithm, and quantum Fourier transform. They are able to work with complex numbers, so if you complete bronze, nickel, and silver, in the end you reach to that point. And in terms of time scales, they are again similar, because each workshop takes around 20 hours, like 15 to 20 hours, and a usual course, usual semester courses again take like 50 to 60 hours. So if you complete these 3 workshops, usually they take around 3 weeks with certain days off, and they kind of take like 60 hours or 45 to 60 hours depending on the pace of that particular workshop and the pace of the instructor. So if you complete all these 3, they kind of correspond to a single semester course in quantum computation. QIntern is a different project that we have, because you also asked related to it something. So let me just share the previous one. Under QIntern, we ask people to first propose projects. So you can actually propose a project as a mentor for QIntern. And after we gather these projects, we check them, of course. And then if your project is, if it is, it makes sense, let's say, in a sense, if it's not pseudoscience, we include it into our call for interns, and we accept applications to the program. There will be a QIntern 2022. And after that, we match these applications to the project proposals. So these can be, you can check the website, these can be very technical projects, or these can be, again, some related fields like assessment of these educational materials, or for example, let me just share this with you. So here is one of the outcomes of one of my QIntern projects. So this is a project called Mapping the Landscape of Quantum Education. And here we gathered quantum educational materials that are existing out there. And we put all of them into a website. And here you can put certain constraints on them, like whether you want certain prerequisites, whether you want courses, summer schools, you do not want any technical things, so they should be non-technical. And here you can actually find different types of educational materials. So this was also a project under QIntern. So you can propose stuff like this as well. And if there are interns that are willing to work with you on this, then it's great. As I said, everything is voluntary, but at the end of this period, you need to present your outcomes. And depending on your presentation and depending on the outcomes of your project, there are some very small prizes that are usually sponsored by different groups sometimes, and this will be the third time we are organizing this, so we are planning some novelties hopefully again, but the general idea is to enable people who would like to work with interns and to enable interns that are looking for projects to work with. So this was the QIntern. And QSpring is just a period that we will organize hopefully many events during this spring period. So it's just a name. So we like putting Q in front of everything. And maybe this is one of the reasons that we are not active in America, because we know putting Q in front of stuff is not welcome much there. Like there's this whole QAnon stuff. So the joke, by the way, we are not affiliated with QAnon.
My comment is, in America, everybody want to teach in their own way and do things in their own way.
Yeah, maybe. And also, there are, as David you mentioned, there are many efforts going in America. I don't know whether they actually need a QUSA, but as I said, we would be happy to help establish such a thing and collaborate with you. And also, one of the things that we were discussing, maybe in this just couple of last minute comments. So during these last 3 years, one of the things that I kind of noticed, and also others in our group noticed as well, that it actually makes a difference whether you come from a country that has a background in quantum computing or you come from a country that is a really newcomer to the field. So for example, let's say there is Q Germany. So one of the things that people from Q Germany can actually do is to, since they already have access to these resources in their home country, they can help people in other countries. So if you are from, let's say, Turkey, then you do not have any quantum computers and you probably have very little access to these knowledge beforehand. So it wouldn't be very feasible to take the QTurkey as a really flagship of anything. But for example, in Latvia, there was this really good group that was under Professor Andres Ambianis, and they, spearheaded this effort because they were involved in the field. They had this really cool network, and they actually were they committed their own time and resources to create this community. So what I'm meaning to say is, if there will be a QUSA, one of the things that people from there can actually do is, in addition to helping this technology or the access to the knowledge of this technology expanding in USA, they can also help other countries or people from other countries as well. They can be mentors, they can be instructors, they can create these educational materials. And one of the things here is that, yes, there are many great materials in English. There are many other languages. And I think USA has a really good diversity in terms of languages as well. So there can be many materials in Spanish, there can be materials in other languages, like, I don't know, French, German, Turkish, Arabic, you know, a lot of languages are out there. And I think efforts from USA can also be really important in this manner.
And one more thing is, can you drop off your work email so that people can follow up with questions for you?
Yeah, sure.
Hi, Jinin, can you ask a question?
Oh yeah, merhaba Zeki.
Hello, merhaba.
Yeah. I apologize. I had a lot of meetings at the same time, so I joined very late. When I joined, you mentioned about the workshop. So if I go to QWorld.net, I'll be able to find the workshop that you just mentioned.
Yeah, so
Okay.
the one that is actually open right now for applications is that will be organized by Q France. So it is there are these activities we call entangling events. They are being used to introduce new Q cousins to the community. So this workshop is the entangling event for the formation of Q France. So hopefully there will be many people from France, but these events are also open to global participation if the Q cousin that is being introduced is willing to. And in this case, hopefully, yeah, so the workshop will be conducted in English. Yeah, okay. I was supposed to check this before sharing, but for some reason I didn't. But yeah, it will be in English, so you can apply. And you can check the website for other events as well.
Yeah, sorry, I accidentally put on mute. Actually, I said thank you and çok teşekkür.
Teşekkürler.
Still have a question? Deb, have you asked a question? Do you have any other question?
No, I don't have any questions. So I think it's all set. So could you send me the slides, Zeki?
Yeah, of course.
Yeah, you can send the slides to me so that I can forward to the participants upon request. And you're welcome to come back with new topics.
Yes.
Yes.
We'll invite you again, you know.
Yes.
Thank you.
Thank you.
Thank you. Have a good evening. Bye.
Bye.